So, I mean, first of all, thank you all for coming. I mean, this is definitely that's the first presentation I've made at NTU so far, and it is great to see so much interest in Ethereum and in the blockchain space in general coming out of here. So, what I wanted to talk about today is start off by giving an overview not of Ethereum or blockchains themselves, but of basically the kind of like the mathematical, technological, and economic principles behind which these networks operate, right? So systems like Bitcoin and Ethereum and things like them, I mean, they are in some ways, they do in some ways share similarities with networks that came before them, but they are also fundamentally different in some certain very specific ways that really didn't exist at all before about 2009 or so. So I'll start off by going over that. Then I will go into in more detail what Ethereum is, and in more detail what kind of things you can do on top of it. Right? So start off with a simple question: what is a blockchain? Now, there's a lot of very simple answers to this. A blockchain is a chain of blocks. A blockchain is a linked list, immutable data structure, blah 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 blah. But I'll give a kind of more functional definition, and this is a definition that does not say anything about what a blockchain looks like, how a blockchain is designed, what algorithms it uses for security. This definition just says what a blockchain does, and it's a simple one-sentence definition. A blockchain is a decentralized network with a memory. Everyone got that so far? So there's two parts to that definition. You might notice there's decentralized network on the left, as represented by a bunch of computers that link into each other, and memory on the right, as represented by a brain. So, first of all, decentralized networks have existed for a long time. Even the internet itself can be viewed as being kind of a decentralized network. Even things as email can be viewed as being partially decentralized networks. And we've also had fully decentralized networks. So, for example, BitTorrent for file sharing. Who here has used BitTorrents to download any kind of file? Quite a few people. Skype, I mean, right now, Skype does have a concept of a supernode, which are basically all controlled by Microsoft, but in its original vision, it was much closer to a pure peer-to-peer network. Tor, so anonymizing internet connections. And there's a bunch of other decentralized messaging networks. There's decentralized networks for lots of reasons. I2P, just lots of different examples. At the bottom, you also have Bitcoin, a decentralized network for currency, Namecoin as a decentralized DNS system, and Ethereum as a general purpose state machine. So we have lots of these kinds of projects around. I mean, and there's also newer things: Mastodon, Twister, various blockchains, Litecoin, Dash, Zcash, whatever. So, this is an area of kind of computer science that is very, very rapidly developing, especially over probably the last decade or so, basically just as computer hardware and computer software technology has finally gotten good enough to the point where we can support systems like this. Now, there's one important insight about these two categories of applications. The second category, so things below my dotted line, is not like the first. So things below the dotted line are not like things above the dotted line. And you might ask, why? The answer is, what does the brain stand for? Memory. So, what do I mean by when I say things below the line do not have memory and things above the line do have memory? Well, let's look at file sharing networks. Let's say I take some perfectly legal file, like an open source Linux distribution, and I send it to you over BitTorrent. I have what is the result? I have the file, you have the file. That was just a series of packets between myself and you, and possibly a dozen other computers in the network. Now, after that file transfer is complete, the network itself does not remember anything about that file transfer. The network itself does not remember anything about whether or not that file transfer took place. right? Furthermore, if I take this Linux distribution and I send it to you, then I send the exact same Linux distribution to someone else. This is totally fine. We do not consider this bad, right? Now, with any kind of decentralized messaging network, it's the same thing. Let's say I write out a message. I say, hello, I am Vitalik, I am sending you a message. And I send this to one person, then I hit copy paste, and I send the same message to another person. This is also totally fine. After I send both messages, the network does not really remember that these messages were sent. My computer remembers, and the first recipient's computer remembers, and the second recipient's computer remembers, but no one else remembers. And in reality, if all three of our computers forgot, everything would still be totally fine. So, the networks that are below the dotted line are different, right? So let's look at just Bitcoin, the currency, as an example. Let's suppose that I have 100 Bitcoins, and I create a transaction that sends these 100 Bitcoins to one person. Then I create another transaction that sends the exact same 100 Bitcoins to another person. Now, either of these transactions is totally valid by itself, but both of them cannot succeed at the same time, right? Now, why? Well, if either of these did succeed at the same time, then I'd be turning 100 Bitcoins into 200 Bitcoins. Now, maybe this could be a good revenue stream for the Singapore government, but if this actually happens, Bitcoin will be fairly quickly become worthless. So, if you want a currency system to work, then basically you want it to be impossible to copy money. And this is one way in which money is fundamentally different from other kinds of information. A transaction of 100 Bitcoins from me to you does not just have to do with me and you. It also has to do with every other person in the community that's using that particular currency who might in the future be receiving those 100 coins. They need to know that you do have the coins after I send the transaction, and they need to know that I no longer have the coins. Now, furthermore, where does the memory come in? Well, the system has to remember that right now I have 100 coins. When I send my first transaction, after that happens, I now have 0 coins. And if I try to send the second transaction, then the second transaction fails, and it fails because the system remembers that now I have 0 coins and not the 100 coins I had before. Name coin, so DNS systems. Well, let's say we'll just take the existing centralized DNS as an example. Let's say I register a website, I register ethereum.org. Then 4 years later, you come along and you see, ooh, this Ethereum project is very popular. Well, I have absolutely no morality whatsoever, and so I am going to try to register ethereum.org myself, and I'm going to use this website to scam people. So basically, you would try registering ethereum.org, and then you would put up your own webpage that says, look, I am selling Ether, just put your credit card number here, and you would try to take people's money. So, if this were to happen, right, there would be 2 attempts at registering ethereum.org. One of which happened around something like November 20th, 2013. The second one happened October 9th, 2017. And if you tried to adjudicate between these two in a system that had no memory, then you would fail. Because after October 7th, 2017, or October 9th, 2017, you would just see these 2 attempts to register the same website, and you have no idea which came first. So if you want to have a system that favors the one that came first, then you need to have a system with a memory. Memory. So the archetypal use case of memory, this is kind of the simplest use case of memory to explain, is basically if in some application you need to know who did it first. So who received a coin first? If I send a coin to B and I send the same coin to C, which of those transactions came first? Who registered a domain first? If I register ethereum.org, then you register ethereum.org to try to scam people. Well, was it I that registered first, or was it you that registered first? Entering into a financial contract. So there might be cases where only one other person can enter into some contract, or it matters when you entered some contract, or it matters when you accepted some clause. Accepted or versus withdrew an offer. Let's say I make an offer to trade one asset for another asset. you send a transaction accepting the offer, I change my mind that I send a transaction canceling the offer. Which one of those two gets accepted first? So these are all just simple examples of use cases of memory. So in order to have decentralized networks with memory, we have to use somewhat different technology from the technology that we use to maintain networks without memory. Now we have to use a lot of the same technology. We still need computers, we still need public key cryptography, we still need a way for these computers to talk to each other. And we still need networks where if a computer sends a message, this message could get broadcasted to the network. But we also need this other ingredient, which is how does the network remember stuff? And in cases of conflict, how does the network come into agreement on what it remembers? So let's suppose I send two transactions. One of them sends 100 Ether to person A, one of them sends 100 Ether to person B. I send these two transactions at the same time. So this is not me trying to defraud A or defraud B. This is just me trying to confuse the network, break it in half, make it so that one half thinks that A has the coins and the other half thinks that B has the coins. Well, the network has to, in some way, come to an agreement on whether it's one or the other. Now, it could be a random choice, but the network has to choose one or it has to choose the other. Being in consensus is more important than choosing, the one that came first, if the one that came first is only 1 second ahead of the one that came second. So, let's look at how these systems are secure. So, this is the slide where I show you the part where a blockchain is actually a chain of blocks. Notice how it's not actually important for describing what a blockchain does. It's only important for describing why a blockchain is secure. So, you have blocks. And each block is like a package of transactions. And you have nodes in the network. And some of these nodes in the network, in Bitcoin and Ethereum's case, these are called miners, create blocks. Every block has a parent. So every block points to some previous block. It says, this previous block is the block that I knew about before, and this is the block that I am creating on top of that previous block. So normally, you would just have this orderly kind of progress where one node creates a block, then at some point you have some new transactions, another node creates a block on top of that block, then you get some more transactions, you wait a bit, then another node creates a block on top of that block, and so on and so forth. And the network just progresses peacefully and it continues adding blocks one after the other, and everything works good. What if it doesn't work out? So there's always the possibility that either because of an attack or just because of regular network latency, you have a branch. Right? So what does it mean when you have a branch? Well, the simplest way a branch can arise is basically if, let's say you have this one block. So you have this block over here. Then, let's say some computer in the network creates this block on top of the block before. Before this block can get broadcasted to the entire network, some other node, somewhere else in the network, still thinks that this block is the head of the chain. And so that node creates this block. Now you have two heads, this and so you have to adjudicate between them. Now, what's going to happen? Well, basically, all of the other nodes in the network are going to see the two heads, and they're just going to randomly decide, do you want to create a block on this one, or do you want to create a block on this one? Let's say we get very unlucky. And let's say we have a node creates a block on top of this block, and at the exact same time, another node creates a block on top of this block. Well, okay, we wait a bit more. Then, eventually, some node is going to create a block, and that block is going to be on top of one of these two chains. So let's say on top of this chain. Now, this chain is finally longer than this chain, and so this chain is considered the canonical chain. And so everyone creates blocks on top of this one, and this chain gets forgotten. So this is something that just could happen in a perfectly normal situation, even if all of the participants in the network are totally innocent. So in general, even creating this decentralized consensus between nodes where all of the nodes are just totally innocent nodes that are honestly following the protocol is still hard if you have even the smallest amount of network latency. Now, the other possibility, of course, is that there is an attack going on. So what if these two nodes are attackers, and they would say that or let's even say that, you know, here you have a chain, and let's say I bought a house from you, right? So or just use to make a better example. Let's say I bought a bunch of gold from you. I bought a bunch of gold. You give me the gold. I send you, let's say, 500 bitcoins for the gold. I take a one-way ticket to Guatemala, where I decide to just disappear, retire with this gold, and where nobody can find me. Now what I'm going to do is I'm also going to try to get my bitcoins back. So here's how I will try to get my bitcoins back. I am going to create another transaction which takes those 500 bitcoins and sends those 500 bitcoins to myself. So it's a transaction just like the transaction that sent you the 500 bitcoins, but this time it sends this transaction to me. Now, in the original chain, there's no way that this transaction is ever going to get in because the conflicting transaction that sent you the 500 bitcoins already got in. So what am I going to do? Well, I am going to get a bunch of nodes, and I'm going to get a bunch of nodes to start creating, blocks on top of here. So we'll say the original transaction was included here. I am going to get a bunch of nodes to start creating a chain over here, include my transaction over here, and I am going to try to get the network to accept this chain. And if this chain wins, then I have your gold, and I have the 500 bitcoins, and I can enjoy my vacation in Guatemala. Now, this is supposed to be hard, right? It's supposed to be hard to defraud someone of 500 bitcoins. So, what are we going to do here? Well, it turns out that basically, if you try to create your own chain, that in order for your chain to get accepted over the chain supported by the rest of the network, you have to, in some sense, have more economic resources than the rest of the chain, than the rest of the network put together. Right? So in proof of work, creating each one of these blocks requires a large amount of computational power, and if you have if you have less computational power than the rest of the network combined, then, well, this chain is just going to keep growing, and it's going to grow faster than your chain, and your attack is going to fail. The only way that your attack succeeds is if you have more computing power than the rest of the network put together. Now, proof of work is not the only consensus algorithm. There's also something called proof of stake that we'll talk about later. But in general, right, the principle is that in order to break the system, you have to have a very, very large portion of the economic resources in the entire network. Now, you might notice that this kind of security model is a very different security model from the security model that existed in any previous system. In a decentralized messaging network, it's not about how much economic resources you have. It's not about how much computing power you have. It's just, I send a message to you, I encrypt the message with your public key, and I also digitally sign the message with my private key. You know that because of the digital signature, you know that the message came from me, and because of the encryption, I know that only you can see the message. So, with this, in decentralized networks without memory, the only thing that we rely on for security is cryptography. Here, cryptography is not enough. And the reason why cryptography is not enough is because there is no purely cryptographic way to say when some message was created or when some message was broadcasted. Right? So there's no if you have a disagreement between two histories, there is no purely cryptographic way of determining which history actually represents the real history. And so we have to rely on other tools. So what tools do blockchains rely on? So this is the kind of package of security technologies that I refer to as cryptoeconomics. Right? So cryptography is used in blockchains, and cryptography is used to provide guarantees about the blockchain's past. So cryptography guarantees transaction validity. So you have digital signatures on every transaction that guarantee that the transaction actually was approved by the sender. And you have various hash linking, which preserves integrity of history. So which basically makes the historical blockchain kind of immutable in the sense that you can't just like go in and like swap one transaction out for another and still get the rest of the network to accept it. Economics provides guarantees about the blockchain's future. So what do we mean about the blockchain's future? Well, what we mean is, let's say I buy your gold and I send you 500 Bitcoins, and these 500 Bitcoins get included here. I want the guarantee that the transaction that gives you the 500, or you want the guarantee that the transaction that gives you the 500 Bitcoins will actually continue to be included in the chain, and that it's not just going to disappear and get reverted. This guarantee cannot be provided by cryptography, and the reason is that it depends not only on the past behavior of the nodes, but also on the future behavior of the nodes. Now, how can we guarantee the future behavior of the nodes? Well, we can give them economic incentives, and we can trust basically that they are not going to follow the incentives, and that they're not going to voluntarily burn huge amounts of money on trying to get the transaction reverted. And we have decentralization. And decentralization basically adds fault tolerance and security. If one node in the network goes down, well, there's still a bunch of other nodes in the network that are producing blocks. If a few nodes in the network get hacked, and those nodes start creating blocks that are off the main chain, well, we still have even more nodes in the rest of the network that will continue functioning normally. So, because of these three things together, basically, blockchain-style networks are secure. Now, notice that, once again, this is a different security model from the security that we have in other kinds of systems. So this isn't kind of ironclad infinite security that says that it takes a trillion years to break the system's cryptography. Now, it still does take a trillion years to break the cryptography of the system, but the economic incentives are different. The economic incentives basically say either the system will keep working the way it's supposed to work, or people will lose a bunch of money. Right? So that's the kind of guarantee that you get. And it's a different kind of guarantee, but as it turns out, it is a guarantee that we can work with. The reason why this kind of crypto-economic guarantee is so interesting is because it basically does create a substitute for what in previous systems would fully depend on trust. Right? So a lot of previous systems in cryptography would depend heavily on some notion of a trusted third party. The system works because, number one, cryptography works, and number two, Bob over there is a trustworthy and nice guy. Now, some people might actually believe that Bob is a trustworthy and nice guy, because Bob is actually some big entity like DBS, and people believe that big entities like DBS have reputations, and so they're not going to cheat you very easily. Now, problem is, not everyone trusts the same Bob, right? Even if there is some Bob that you trust, there's probably some different Bob that you don't trust. And the Bob that other people trust is probably not the same Bob that you trust. And furthermore, if you are some Bob who's a college student, and you're just trying to make an application, and you're trying to convince lots of people to trust it, well, guess what? You're just a college student. You're a Bob that nobody trusts. So it's useful to have systems where the security of the system does not depend on trusting any specific person. And so instead, what do? Well, for technological reasons, it's impossible to build systems for many applications where the trust model relies purely on math. But what you can do is create systems where the trust model relies purely on math and economics. So how does this work? Well, basically, in these kinds of systems, you have economic incentives that reward participants who further the system's objectives and penalize participants who harm the system's objectives. So, in this kind of system, basically everyone is incentivized to act pro-social, and everyone is disincentivized against acting anti-socially. Now, we don't trust every Bob, but we do trust that almost every Bob likes money. Even Bob in North Korea likes money. So, incentives and proof of work, right? So, first of all, there's basically three things that a miner in a proof of work system can do. One of them is they do not participate. If you do not participate, you get a reward of 0. Make sense? Who here does not understand the idea that if you do nothing, you get a reward of 0? Okay. The second thing that you can do is you can create a block on the main chain. So basically you have the main chain over here, and you just create a block on top of the chain. You would create another block over here, and your block would become part of the main chain. Your reward is going to be, basically the system automatically assigns you a reward of 12.5 Bitcoins. Now to create the block, you have to pay some cost, some electricity and some hardware cost. But if you have good hardware, then the expense is going to be less than 12.5 Bitcoins, and so you make a net profit. Now, what if you create a block that is not on the main chain? So you create a block over here. Well, because this block is not part of the main chain, you do not get a reward, but you still have to pay the cost, right? So you still have to pay the computational cost of creating a block, but you do not get 12.5 Bitcoin reward. And so what this means is that you get the penalty and not the gain, and so you lose money, right? So if you do nothing, your reward is 0. If you act pro-socially, your reward is positive. If you act anti-socially, your reward is negative. So basically, this is actually a very kind of philosophically interesting thing. And the reason is that Bitcoin is basically, and Ethereum are systems where the security of the system itself relies on economic incentives that are defined only inside of the system itself. So you have this weird kind of recursive feedback loop where basically the rules of the system itself are what maintains that system and that system's ongoing continuity, and therefore the continuity of the incentives themselves. Now, it might seem like a circular argument, but I mean actually it's an inductive argument, right? We already know the system works now. Therefore, people expect that the system will work in the future. Therefore, there are incentives, or at least people think there are incentives. Therefore, the people will actually act in pro-social ways. Therefore, the system continues existing one step in the future. Therefore, there actually are incentives one step in the future. And then from there, exact same argument for step n plus 2, same argument for step n plus 3, and so forth. Right? Now, this actually is, this is probably a more complex than usual way of explaining why it works. But in some ways, it is extremely kind of mathematically and economically clever. So, crypto economics as an idea does have a lot of applications going beyond just blockchain consensus, right? So we can talk about things like scalable verified computation. Basically, the idea is that we can use economic incentives to create supercomputers whose computations don't get run on the blockchain, but do get verified by a blockchain. We can create scalable blockchain protocols. We can create protocols that only use blockchains in some specific contexts, and under normal circumstances don't use blockchains. So you can create systems that use blockchains only some of the time, but because of the way the systems work, they still have the full kind of economic security backing of the blockchain. And so they have almost the same security as though they use the blockchain all of the time. I mean, there's different ways of getting scalability. You would have there are other applications, so there's things like oracles, there's things like provably fair random number generation. There's a lot of applications for kind of crypto economic systems that exist on top of blockchains themselves. But the first app of crypto economics is actually maintaining the consensus of these networks themselves. Right, so once again, what do you get? What do you get as a result of all this? You get a network which is fully open, where anyone can participate, and where the security model of the application or of the blockchain does not depend on trusting any particular model. This is all pretty good, right? So let's start talking a bit about what these systems can be used for. So the thing that a lot of people talk about is something called smart contracts. Now, the thing that even more people talk about is cryptocurrency, but I'm going to trust that people here roughly know what cryptocurrency is. So I'll skip straight to the more interesting stuff. So, what is a smart contract? So in the narrow sense, a smart contract is a computer program on a blockchain that controls digital assets. So it's a computer program where the execution of the computer program is kind of run and mediated by a blockchain, where this computer program controls digital assets that are on the same blockchain. Now, in the broad sense, a contract is just an application on a blockchain that accepts transactions and interprets transactions according to certain rules. The concept of a smart contract was originally created by Nick Szabo back in 1994, and the analogy that Nick Szabo used was vending machines. So, what Nick said is this. Let's take a look at a vending machine. A vending machine is a system in physical hardware that implements basically the rules of an agreement. What is that agreement? Well, the terms of that agreement are simple. You put $2 in, water comes out. You do not put $2 in, the bottle of water does not come out. So, fairly simple set of rules, but basically this big box implemented in hardware basically implements and enforces those rules with some degree of security. Now, vending machines, so contracts in the physical world are fallible, right? If you really wanted to, you can knock the thing over and you can get everything inside of it for free. But, so, there is a limit to the security of these systems, and so they're okay for $2 bottles of water, but this is probably not okay for $20,000 bars of gold. Now, a smart contract is bringing the exact same concept into the digital world. Now, in the digital world, we do not have security based on metal. We have security based on cryptography, and cryptography is a kind of armor so powerful that even messages that are signed and encrypted by regular individuals are secure enough to resist being broken by nation-state level actors. And so, in the digital world, yes, we can have computer programs that, like virtual vending machines, secure $2 million worth of assets, and it still works. So a computer program that directly controls digital assets and distributes them according to a pre-specified set of rules. That is a narrow sense smart contract. So let's start off by going a bit into the process. So once again, everyone is bored of cryptocurrency, so we'll take another simple example, which is, let's say we want to use Ethereum to make a decentralized domain name system. So instead of registering some website.com or some website.org, you would register some website.eth, and this registration would go on the blockchain, and any user that downloads a specialized plugin would be able to access these .eth websites. So this is what the code of a contract that implements a simple domain name system would look like. So this is a contract that's written in a language called Viper. It's a high-level programming language, so you can write your code in this high-level programming language, then you can compile the code, and the code will be compiled into a much more kind of compact, low-level form called EVM code. The EVM code would get uploaded onto the blockchain, and then the EVM code would get executed on the blockchain as part of the process of verifying the transaction that creates this contract, and then any transaction that represents an operation that interacts with the contract. So let's look at the contract's code. So first of all, you have, at the top, the declaration of what the contract storage is. So this is kind of the mutable state of the contract. This is stuff that the contract remembers. So basically, it's a map, and it's a public map, so anyone can read it, but that doesn't matter. Then what the map does is it basically says, for every domain, and we'll say domain is a bytes32 object, it's going to store what IP address the domain points to, and what address is the owner, right? Now, we're going to have three functions. One of them says register. And if you want to register a domain, anyone can register a domain. It checks that the domain does not yet have an owner, and it just sets the owner of the domain to be the sender of the transaction that made this function call, right? So if a domain has not yet been registered, then you can register it. Second function, set IP address. If the sender of this transaction owns the domain, then they can set the IP address of the domain to whatever they want to set it. Set owner. So this is the third function, and it basically says, if you own a domain, then you can change the owner to whoever you want. And so this is just like a simple, very minimalistic kind of DNS-like system on the blockchain. Now there is something called ENS, which is a kind of much more advanced version of this, which actually has been running on Ethereum for the past 3 months, and there have been something like hundreds of thousands of names already registered on it. But this is like basically the core of how the thing works. Now, let's take a look at a smart contract in the Nero sense. Unfortunately, the code got formatted weirdly, but oh well. So what we can do, so what is this? Basically, this is a 2 out of 3 escrow system. So the story in 2 out of 3 escrow is this. Let's say I am buying a bunch of gold from you for, we'll say, 500 ether. Now, there's 2 simple ways of doing this. The first one is, you send me the gold, I send you the ether. The second one is, I send you the ether, you send me the gold. Both of these are imperfect because both of these require one of us to trust the other. If you send me the gold, you have to trust me to send you the ether. And if I send you the ether, I have to trust you to send me the gold. Now you could do arbitration where I send the ether to a third party, then you send the gold to me, then the arbitrator sends you the ether. But then we still have to trust the third party. When I send the third party the ether, the third party could just run away with the ether. Now what we can do here is we can make a smart contract that reduces the need, the extent to which you need trust from basically a system where one person can run away with money to a system where you need 2 people to collude to run away with the money. So here's how it works. Step 1, I send the ether, but I do not send this ether to a person. I send the ether to a computer program. And the computer program is a smart contract which is running on the blockchain, and it has this code. Now, when I send the ether, I specify who is the seller. So I specify who is the intended final recipient of this ether. And I specify who is the arbitrator. So if there is a dispute, who decides? Now, all of these values get saved as part of the contract's memory. Then what we have is we're going to have 2 functions. And the first function is refund. So refund basically says, if you, the seller, decide that you cannot send me the gold anymore. So let's say you just decide, maybe I want to keep the gold, or maybe all your gold gets stolen, or anything happens. Then you can just decide, you're going to voluntarily admit that you cannot satisfy the terms of the deal. And so you're going to call the refund function, and you're going to give me the money back. There's another function which is finalize. And the logic of the finalize function basically says, if I receive the gold, then I can send a message that says, I am satisfied that I received the gold, and this basically sends the money in the contract to you, the seller. So the line that's kind of hidden here basically says, send but to the balance of the contract, but to the seller instead of to the buyer. Now, what if so basically we have these 2 functions, right? So refund can be called by the seller, and it sends the money to the buyer. Finalize can be called by the buyer, it sends the money to the seller. What if we disagree? What if you decide that either you're going to cheat me, so you're not going to send me the gold, but you're going to claim that you sent it, or you do send me the gold, but I'm going to claim that I did not receive it? Then, well, the finalize and the refund function can both be called by the arbitrator. So the arbitrator, as a third party, can judge, was the gold actually received? And they can decide, are they going to send the ether to the seller, or are they going to refund the ether to the buyer? Now, notice that we do not trust the arbitrator to do everything. The arbitrator themselves does not have the ability to take the money for themselves. And so the trust model here basically says, if the buyer is dishonest, then the arbitrator is going to give the money to the seller. If the seller is dishonest, the arbitrator is going to give the money to the buyer. And if the arbitrator is dishonest, well, their only moves are to give the money to the seller and the buyer. And if the 2 of them are honest, then they're going to give the money to the person who deserves it. In order for the system to break, you would need 2 parties to both be dishonest and collude with each other. So this does not perfectly remove the need for trust, but it reduces it. Now, let's say instead of selling gold for ether, we are going to be selling a domain name on the Ethereum blockchain for ether. If you do this, then you actually do not need a third-party escrow, and you do not need any trust at all. You can make what's called a fully atomic swap, right? So the atomic swap basically is you have a smart contract, and what we're going to do is, number one, we're going to launch the smart contract, so publish it to the blockchain. Then what we're going to do is we are going to use the set owner function, and we're going to transfer the ownership of the domain to the smart contract. So the owner of the domain actually becomes this computer program. Now, this computer program has two functions. One of them is buy. So if anyone else wants to buy the domain, well, they can send a transaction, and if this transaction also contains at least 1 ether, then it actually does basically transfer the ownership of the domain to the buyer, and it sends the seller the money, right? So basically, if someone buys, then they get the domain and the seller gets the money, or the seller can call cancel order and they get the domain back. So if someone buys, then the domain and the ether get atomically swapped for each other, and if this does not happen, then the seller can get the domain back. So in this way, you can transfer one kind of asset you can trade one kind of asset on Ethereum, the domain, for another kind of asset on Ethereum, 1 ether, and you can do this in what's called an atomic swap. So the word atomic here comes from the Greek atomos, which basically means uncuttable, right? So you can do both parts, but you can't do one part without doing the other part. Either the ether transfers and the domain transfers, or neither of them do. And this is just another example of like how smart contracts on a blockchain can increase the security of trade. So, just to step back a bit, what is Ethereum itself, right? So, the definition of Ethereum that I usually use is Ethereum is a general purpose blockchain. So, Bitcoin was a blockchain for digital cash. Namecoin was a blockchain for decentralized DNS. Mastercoin was a blockchain protocol for doing a few types of financial transactions. Ethereum is a general purpose blockchain. So it's a blockchain that can run computer programs. So all of these examples that I showed are real computer programs that can be executed actually compiled and executed on Ethereum. And you can see, you have here a computer program for a decentralized DNS system, here a computer program for doing escrow, here a computer program for selling a domain name. So you can do pretty much, any of these things on Ethereum, and it's basically any application where you can define the business logic of the application in code. That is an application that you can write as a smart contract, publish a smart contract on Ethereum, and run as an Ethereum application. So here's how Ethereum works for you, the developer. It's pretty simple, right? Step 1, you write code. So you write this. Step 2, compiler compiles code. So there's a compiler, and the compiler converts the Viper code or the Solidity code or the LLL code or whatever language you use into EVM code. It basically compacts bytecode. Step 3, you send a transaction which contains that code to upload the code to the blockchain. When the transaction is confirmed and when the code gets uploaded, the system generates an address and it creates a contract at that address. And the address might look something like this. Now, this isn't an actual contract address. This is actually an address that corresponds to the private key, which is the hash of the word cow, but I'll just not talk about that right now. So basically, if you have a contract, that contract has some address, then anyone can send transactions to that address in order to interact with this application. So you might notice that over here you have, basically it looks like a piece of code that has these functions as kind of entry points. The way that you would actually call these functions is you would send a transaction. The to address of the transaction would be the address of the contract, and the transaction has an extra data field, and the extra data field encodes which function you're calling, and it also, in this case, encodes what the arguments of your function call are. So that's what it would look like for you as a developer. This is what the Ethereum network looks like. You have about 25,000 nodes all around the world, a bunch in North America, a bunch in Europe, some in Asia as well. And you can see Singapore is the most significant dot within something like a 2,000 or 3,000 kilometer radius. Congratulations. So, yay, the Ethereum network. It basically is just a bunch of nodes that are talking to each other. So how does Ethereum work for you, the user, right? So every operation, everything that happens inside Ethereum is a transaction which gets recorded on the public blockchain. You can check this transaction on an Ethereum client, or you can look it up on a Block Explorer, right? So for any transaction that you do, there are sites like Etherscan, there's another one called Etherchain, there's another one called live.ether.camp, where you can basically check the details of the transaction, check the execution of the transaction, check what effects the transaction had, check what it caused, whether or not it succeeded, and when it was confirmed. So, this is a public blockchain. Execution of everything on the public blockchain is open and verifiable by anyone. And if you run a client, you can verify the presence and correct execution of any specific transaction. So now, if you're a non-technical user, you don't have to worry about all of this, right? If you're a non-technical user, then interacting with an Ethereum application basically just looks like downloading MetaMask, which is an extension to Chrome, and then just browsing your decentralized applications just like you would browse websites. So if you just want to interact with the blockchain on a service level, it's easy to do that as well. That said, if you actually want to kind of dig down and really get the kind of full assurances of decentralization, which basically means that you can verify whatever you want for yourself, then there are a bunch of tools that, with varying levels of difficulty, varying levels of security, that let you do that as well. So, if you want to start building things, right, then basically tutorials at ethereum.org. If you want to download a client, then basically an Ethereum client is this kind of node in the full Ethereum network. So you have Go Ethereum, Parity, Ethereum Jade. There's about 7 of these. If you want to start writing smart contracts, then you would write you could use Solidity, Viper, and for testing you could use Ethereum Python client. So there's a lot of stuff that you could use. Now, as far as what people actually are using Ethereum for. Unfortunately, the slides once again got a bit corrupted, and there was something missing here. But basically, there's a site that has, various different blockchain Ethereum applications. And I will say that over the last, especially 6 months to 1 year, both inside of Ethereum and outside of Ethereum, the number of applications that it has been used for has really increased substantially. So, one example, there's examples in almost every industry, right? So there's a bunch of financial applications, and by far the simplest financial applications is just issuing tokens, right? So basically, on Ethereum, anyone can issue your own cryptocurrency in about 45 seconds, and your cryptocurrency that you just issued will be based on top of a platform that will have more security, so much security that it'll take there's no way that you could possibly match it with a purely centralized system. Now, and this is being used for blockchain protocol tokens. There are people making tokens that represent things like gold, dollars on the blockchain, various assets on the blockchain. There's people trying to do various financial applications. So there's this idea that you can use smart contracts to do blockchain-based insurance. So the nice thing about financial contracts is that they actually are a kind of contract that's fairly easy to represent in a computer program. So if you think about things like, this escrow system here, there's a lot of applications where you kind of can do something like this, and you can approximate the kind of security that you get from this kind of model. Right? So that's one thing that you can do. Another thing that you can do is also various kinds of non-financial applications. So DNS is one simple example. Another very important one is just everything to do with authentication and identity management. So if one kind of, I had this list of applications of use cases of memory here, and one that is unfortunately also kind of below the slide here is basically revocation versus use of a key, right? So the problem here basically is, let's say you have an account and you use this account to authenticate yourself to some service, and quite often you want to have a key revocation scheme. So you want to have a scheme where if some particular key gets compromised, then the key can get revoked and you can switch to another key. Well, let's say that I am interacting with some website, and I use some key to authenticate myself to the website. How does the website know whether or not this key is still valid, right? So there could have been a revocation that was signed, but how does the website know that there actually was a revocation? Now, what you could do is you could just have a regular decentralized network, like a file storage system, where if I want to revoke a key, then I could just send the revocation. The revocation would get broadcasted across the network, and hopefully everyone would hear it. But what you really want for security, right, is that what a lot of people talk about blockchains to do things like proof of existence. So proof that some message was signed at some time. What blockchains are even better at is proof of inexistence. So with a blockchain, you can very easily prove that a message of a certain type has not yet been sent. And so how does this work? Well, basically, you would publish, if you want to revoke a key, you would publish a key revocation as a transaction that would go onto the blockchain. And if you want, some website wants to check whether or not some key is active, well, they would look up, some smart contract that stores the revocations, and they would check, has there been a revocation sent for this particular key yet? If there has, then they would just say, you're not allowed to use this key anymore. And if there hasn't, then they would know that the key has not yet been rejected. So there's a lot of these kinds of fairly small non-financial applications that exist for blockchains as well. There's also very kind of esoteric ones. So for example, in the pharmaceutical industry, one problem that a lot of people have is if you get a prescription, then people would often kind of double spend the prescription, so they would use it at 2 different pharmacies, or possibly 50 different pharmacies. And one of the kind of applications that people are thinking about is basically any one of these prescriptions would actually have a kind of cryptographic key, and when you use the prescription at one pharmacy, then the cryptographic key would automatically get uploaded to the blockchain, and it would basically get stored as a revocation. And then when you end up going to a second pharmacy, it would already see that basically that particular prescription has, in some sense, already been spent, and so you can't use it again. So there are applications, like small applications like that, across a bunch of different industries that people are starting to use blockchains for. And this ranges from just interest interest among just individual small developers. So there's interest among there's various big companies that are trying, in some cases governments that are trying to experiment with things like this. So it actually is a fairly versatile tool in a lot of cases. And the cases where the tool really shines best are the cases where you want to have applications that do not depend on trusting any one person, right? So basically, applications where either there is no central party that everyone trusts, or applications where you could create a centralized party, but it would be better to try to create an application that gives you the same efficiency benefits as a central third party without actually creating what's basically a monopoly in the middle, right? So, there's applications for this, especially in the finance industry, where you could do things like facilitating interoperability between payment systems. There's various smaller applications like this in the supply chain space. There's basically verifying the integrity of supply chains, verifying the source and authenticity of products, just verifying what particular documents have been signed, verifying that some messages have been sent versus not being sent. So there really is a lot of this, a lot of these kinds of things are pretty much almost anywhere. So if any of you are interested in starting to develop blockchain applications, then I definitely encourage you to look. First of all, look up things that already exist. If you want to know, the website is dapps.ethercasts.org. So dapps decentralized apps, then ethercasts etherpodcasts.org, or Mikey.com, I forget. And just look it up on the internet and see what people are building, and see what you can build yourself. So thank you.